Maybe. We should be recording. Okay. But I need to share the screen over here. Let's be smart, smart, smart. We go here, we share the screen. We float. We float. We float. We are floating. All right. So let's continue with two-way tests. As a quick reminder, Amanda, what's a two-way test? How many test variables are there? How many variables do we think might be having influence when we do a two-way test? Two. Yes, exactly. Exactly. And Jimmy, could you give me an example of a two-way test? Maybe something we could compare that would be a good indicator of a person's final grade. Yes, so what's something that might influence a final grade that might be of interest? Attendance, yes or no. Jamie, give me another categorical variable that could influence final grade as an example. Study time, none, a little, some, a lot. Two separate categories to which we might want to look just at the main effects, where we just look at attendance, and then we just look at study time, or we might want to look at their interactions, where we look at attendance, study time, and the interaction between the two. Make sense? Two-way tests. Why, Julie, is a two-way test better than a series of one-way tests? Why can't we use, Jamie, and just say, but all I want to do is a two-sample t-test, compare whether you attend or not and how that affects final grades. And then I want to do another test where I want to do a K sample test, like a one-way ANOVA, and look at how study time influences with final grade. Why is that sort of less ideal than a two-way test? I love that. One, I love pragmatism. More convenient. That's awesome. I wouldn't describe that normally, but I think you're dead on. It's just simply more convenient. But then two, you reduce your probability for error. There's a third very important thing. A little louder, a little louder. It's actually a third one I really hadn't thought about, and that's the fact that you could have confounding variables. You can have two variables that are basically describing the same thing. If you test them both independently, they both look influential. If you separate them out, you can actually see which one is having the effect. Lauren, I saw your hand as well. The interaction term. I love those. I had thought of two. You came up with four. Four is more than two. That is good. Excellent. So these are just some of the reasons that a two-way test is nicer and more valuable for us. Well, nope, wrong computer. There we go. We can also use a two-way test. And by the way, you actually may want to get on Zoom today because Sean can't join us in person. Sean decided that he was going to break his car this morning. I don't know why. Seems kind of weird. I agree. I see some head shaking. Why would you do that? And he's now stuck at home because he doesn't have a car. And Sean, that was with air quotes. And therefore, he is joining us through Zoomland. But for people on Zoomland, you definitely got Sean's attention all the way through. So call him out and make him help you, right? Other people, if you want to grab Sean, he will be online. But another type of two-way tests are repeated sample tests. And these are very much like our paired test. If you remember our paired test. And Misty, can you give me a little reminder of paired test and what a paired test is? When you have dependent data, that was beautifully stated. We have dependent data where the data you sample includes the same individual twice or the same sample twice. good example is pre and post. You do the person pre, you come back and you do that exact same person post. Before treatment, after treatment, very common thing used in ecology and medicine. You look at the condition pre, and then you come back and you look at it post. You might look at it relative to age, where you look at the immature individual first, then you come back to that same immature individual later. There's this whole cool field of epigenomics going on, where they're looking at things like how survival during the Great Depression affects heart disease in individuals of the same genetic inherited group. Yeah, it's so damn cool. Where in one example, individuals who were from the elite class of Swedes, because Swedes are primarily Lutherans, and Lutherans collect very good data about their congregants who come to church. If they were elite, they did not suffer through a starvation period at the turn of the 19th century, no, 20th century, sorry, early 1900s. If they were not elite, they suffered through this starvation event. 2 generations later, that was directly related to the probability of heart disease. And weirdly, it was the people who were related to the elite individuals who had food who had higher likelihood of heart disease independent of other categories. These are genetic tags that are getting inherited from one generation to another, definitely paired. Now, cool, pre-post. Cool, early, late. Cool, before treatment, after treatment. But a lot of times you got more than one step that you want to take a look at. And you can't do that with a traditional paired 2-sample test. So that's where repeated samples can become very nice, where you can now look at it over multiple steps. The first occurrence, the second occurrence, the third occurrence, the fourth occurrence. That makes sense? And you can look at changes or not changes during that period of time. So we're going to use an example from a study, which we did in 2019, and we repeated over this past summer, that was looking at the biodiversity of reptiles and amphibians in the lowland Peruvian rainforest. All right? The work was done in something called Santa Cruz Forest Reserve, which you can see right here. It's right next to one of the rivers and tributaries of the Amazon called the Amazon. The Amazon River is a big river, you know, by Florida standards, freaking huge. By Amazon standards, it's like a creek. You know, I'm not even sure it gets to be a creek. It's just a creek, it's tiny. This forest reserve is about 10 kilometers by a crow's flight from Iquitos. I think I mentioned Iquitos before. This is the largest city on the planet. It's not directly connected by a road. The only way to get to Iquitos is by boat or by flight. And Iquitos is 2,000 miles inland. It is the furthest port away from an ocean, in that you have seagoing vessels that come into Iquitos, drop off their cargo, pick up cargo, go away from Iquitos. Process that again, 2,000 miles. And this is the Amazon. And the Amazon is not a creek at this location. The Amazon is 2 miles wide. 2 miles wide, 2,000 miles away from the ocean. Just try to process that, because our big river, what's our big river? No, our country's big river, the Mississippi. The only thing big about the Mississippi is the number of letters. The Mississippi's like a midget by comparison to this thing at Iquitos, not the actual delta, which is many, many thousands of miles away. Okay, so what we did, we were interested in the diversity of amphibians and reptiles relative to things like primary, secondary, and pasture environments. Primary forests are things that have no evidence of being disturbed by humans. Secondary forests are forests that have been restored in this case, or allowed to return once humans move out of that location. And pastures are the last stage of the forest, the agricultural system used in the Amazon, where a lot of slash and burning is used. What happens, slash and burn, soil is very good for a few years, get a lot of good crop harvest out of it. The soil gets depleted very quickly because there is no soil in the rainforest. You go into the rainforest and you scrub through the ground, there's no soil there whatsoever. It is hard, compact clay. Why is there no soil in the rainforest? It's weird, isn't it? It's kind of effed up. So in a rainforest, what are you telling me? There's no soil? I'm saying no soil, none. Why is there no soil in the rainforest? You're a biologist. What's that? Could be saturation water, but it's clay. Clay. And what does water do? Not doing clay. Does not drain. Not at all. Why is there no soil in the rainforest? Could. Doesn't get washed away. I mean, it does get washed away, but it really doesn't get washed away. It does, but not really. Rainforest is hungry. There's so much life in the rainforest. Anytime something decays, it is immediately reabsorbed. In fact, most things end up decaying before they even hit the ground. And as soon as they hit the ground, they're gone within days. So you got a constant flood of leaves going down, but it's never getting a chance to actually decompose where it becomes soil and stays within that area. The nutrients get taken back up immediately. So it's a brilliant system. And we want to look at, again, primary, secondary, pasture. To do this, what we did, oh, no, you don't see that much. You see this one over here. To do this, what we did is we would do transects, looking for these animals along different forest conditions. And for each transect, we did it 4 times during the course of the season. And we got some really cool results. A few things that we're able to identify is based on the community structure, we can identify that the primary and secondary forests had very similar biodiversity. There's something called a canonical correlation. If you ever want to take advanced biostats, we'll talk about this. But what you can tell by the first axis, the x-axis, the primary and secondary are basically on top of each other relative to that axis. Tremendous amount of similarity. The pasture environment, not surprising, open landscape, very hot, dry, very different biodiversity, as you can see by the distance on this first axis. Relative to the second axis, you can notice that the primary, the secondary, and the pasture all end up being different. So there are unique properties in the primary, community ecology, that make it different than the secondary, that make both of them different than the pasture. That's awesome. We're also able to do things like biodiversity indices using hill numbers, which allowed us to not only define how many species we saw or the biodiversity that we measure, but then model out and interpolate what we would have found if we were able to fully sample the system. And therefore, as you look at this, you can see solid lines. That's actually what we find. The cloud around is a 95% confidence interval that if we were to redo this, this is the range of what we would find up until that many animals sampled. And then the dotted lines that go from there are the interpolation based on the model from projection about what we would have found had we continued to collect up to, in this case, 1,000 animals. It's able to do that because it actually kind of makes a lot of sense. If you go into the forest and you sample 10 animals, and they end up being 10 different species, you know you have 10 species there at least. If you go back in the forest and you do another sample and you get 10 more animals and 2 of them are repeats, you're starting to get some redundancy. If you go back in the forest, by the 5th time, you're only seeing those 10 species, you're pretty confident you're not going to see any more. And therefore, after a few times, you're pretty comfortable that you've got a full representation of the system and you get something that looks relatively flat. If you go back into the forest, though, and each time you sample, you're always picking up new species, random species you haven't seen before. Maybe it's a ramabone, maybe it's a bushmaster, maybe it's a little, dart frog. What's a dart frog? And every time you go out, there's something new. You know that even though you've sampled exhaustively and you've sampled hundreds upon hundreds of animals, there is still more to find. And that's a good example of where we're looking at the primary here in green. We found this many, but because we keep finding rare species, our expectation is that this is going to continue increasing even after more than 1,000 animals have been recovered. This is great. There's some good information in here. This made us happy. Sure. It's called a canonical correlation. It's a type of factor analysis, principal component analysis, which could be one of your 2 choices for the topic that you guys play with. And what it does is it measures unmeasurable latent variables based on the relationship between those things that have been measured. So what this does is it says you found these things in these environments. How often do you find them only in those particular environments relative to the other environments you could have tested? Were they evenly distributed across all 3? Were they localized within an individual? And how does that compare relative to the other animals that you sampled over that period of time? There are n classes of correlation, of which we are looking at here the first, the most important, and the second most important. What you are really looking at here is a visual representation of what you should see as stacked bars. So when you see primary and secondary, this is basically occupying the exact same space along the x-axis. So they are essentially the same along this variable that is the largest contributor to explaining the model. There's no numbers here. There's a lot of numbers that go into it. That's how we're reporting the figure. This is a visualization of that information. Each dot describes a species associated with its primary habitat and the distance it is mathematically from the center of that variation. So dots that are relatively close are very close to that overall community structure associated with, in this case, secondary forest. Dots that are vertically up and down are very well described by the first axis of variation, but not the second one. Dots that are going to the left and right are better described by the second axis of variation, but not so much the first one. The second variable, the second latent variable, again, something we can't measure, is the second source of variation. In this case, we're looking at these as basically columns where primary, pasture, and secondary are all separated from each other. So the first variable describes similarities between pastures and secondary. The second variable said that there are also those differences, not as important, but they are still present. And that's kind of cool. This makes us happy. Are you happy? Am I happy? Are we happy? There is joy in this. So not only do you get to learn some information, but you get a little bit of enticement in case you're like, I do need to geek off more. And when that becomes available, you can geek off more. But, oh, sorry. No, I want to make a difference. Sign doesn't really matter in this case. Yeah. It's a graphic representation of the community structure. Yep. We're happy, but we're concerned about the study. And we have a problem that we need to determine whether it's a problem we need to pay attention to or we can ignore. And that is, we went back to each one of these transects multiple times, and we measured the same space. And what we need is consistency over time. What we need is a situation where we don't have a seasonal effect. What we need is that the community needs to be stable during the course of the study so that we're not having a confounding problem associated with seasonality. So we need to do a repeated sample, and we need to have a null hypothesis as our measurement to ensure that our methodology isn't getting confused by season effects. Does this make sense? Does the concern make sense? Oh, is there? Do you think Sean's answered it? We'll find out. The question is for fun, which I don't know what that means. And are you recording? And yes, Seth, I am 90% sure I'm recording. Yes. What's that? Oh, yes, of course he did. Of course he did. Question so far with the problem? Why we need to do this? Okay, so these are the results. This is what we care about. But a lot of times you have to do statistics to make sure that your study is actually telling you what it's telling you. So this is a methodological statistic. This is not something that you would report. But in this case, it was important to this study. And we needed to look for seasonal effects. And we were hoping not to see any. That's what we were hoping. Otherwise, our story is more confusing and we have to take more effort in trying to separate out where the variation is occurring. So what we do is we do a repeated sample. In terms of the model, it's still in ANOVA. Whoops. In terms of the model, it's still in ANOVA. In terms of getting a variable name, it works perfectly. We have a test variable. And we'll talk about that in just half a second. And what we need to do is we need to evaluate our model. And then we need to control for the repeated sampling. That is our error and blocking effect. And then we sort of draw out our DF and we draw out that. What I want you guys to do is I want you guys to download the Peruvian data. I want you to set up your project. I would use the same project I did before, 2A. I would just make a new script within there. I'd make sure the data are CSV. We may stop in half a second if there are questions about what are these data. And then once you get there, we're going to need to know what these data are so we can figure out what we're actually modeling, all right? And then we'll compare that relative to our repeated sample. Now, the repeated sample is going to be site, primary, secondary, pasture, site variable, relative to replicate. And we did 4 replicates for each transect. A, B, C, and D. Let's go and get started with that. I'm going to put this slide up for a few seconds. No, I'm not going to do it. Sorry. I'm going to put this up for a few seconds. I'm highlighting this information to help you figure out the aesthetics, because that's your aesthetics. Okay, I'm going to put it back in the PowerPoint. Put the aesthetics and the initial part of the plot up on the screen. One of the things you'll notice is that the fill, we're not actually establishing any aesthetics. The fill, we're going to establish down in the summary and the error bars going through. So instead of putting habitat as fill up in the aesthetics, we're identifying the Y and the X, and then we're actually going to address the colors and the groups by which we're going to do the mean. And that's the beginning start. I'll show you guys the text only. A lot of people get caught up. Okay, the last part of the code is that alpha in the legend is annoying. So get rid of it. Scale underscore alpha, parentheses guide equals none. We'll get rid of it. Last is you should always update your accesses as needed. And species richness, all one word, obviously is a problem. We used a confidence interval in order to do it. And therefore, you should modify it. Oh, trying to go the right way. And such. One of the things I hope you guys are seeing is the code can look daunting, and it can, but it's really highly redundant. You know, line 71 through 73 is exactly the same as line 74 through 76. There's no difference in that code, except in one case, we're defining the properties of the line, and in the next case, we're defining properties of the mean. It's still the same alpha, still the same size. Well, I guess not size, sorry. But the jitter dodge, the same. The next line, a little bit different, not dramatically, still habitat. But now our function is mean confidence interval, and we're bootstrapping our confidence interval. Confidence, I don't know. Good question. I just know it works. Yeah, good question. I don't know. All right. So we run it all. And I'll put the stuff that's down the bottom right here, lines 80 and 81 are the parts that we just showed up. Okay, so visually, are we able to confirm our issue? Is there a difference between the replicates? Is there a massive difference between species richness in A, B, C, and D? Are they basically the same? Visually, are these looking like they're the same? The amount of richness in A, the amount of richness in B, C, and D. Don't be seduced by the means. Pay attention to the variation. Are they the same? Absolutely, they're the same. The variations are very large and overlapping between the four replicates. Notice I'm not talking about the lines at all. We know the habitats are different. That's not what we're addressing here. Do we see a change by replicate? And the answer is no, we really don't. The replicate stays the same all the way through. What about the interaction between the replicate and the habitat? So as an example, are one of these lines going up and the other line's going down? In that case, the replicates would stay the same, but you would have an interaction term. Do we have a case where like pasture's going up and secondary's going down? Or do they all kind of stay the same on the same basic line all the way through? It's kind of the same basic line all the way through. So one of the things I've tried to do all semester long is introduce you to some data where what you expect, what you would think, based on a question, you're going to have to describe the alternative. There's a difference, there's a relationship, there's a correlation, there's a regression. But I've also tried to provide you data where we actually expect the exact opposite, where we expect a null to be true. Sometimes because we have a procedural issue, that's what we have here. Just a methodological question, just a methodological confirmation for the overall study, where we don't want to see a methodological issue that confuses the interpretation of the data. But in this case, what is the hypothesis we're hoping for? Is it the null or the alternative? It's a null. We're hoping for the null. In this case, we're hoping for the null. In this case, we see that. There's no difference between replicates, and there's no interaction term between replicate and habitat. Are there differences between habitat? Are some habitats more and less than the others? Of course, absolutely. Pasture is much smaller than both secondary and primary. We see that mathematically in our results, and I'll go back up to that. Habitat, that's a tiny p-value. We describe the alternative, but are we going to use these data to describe that pattern? We're going to use this analysis to describe that pattern? No, we got all this sexy stuff over here. We like this stuff. That's gorgeous. Those numbers are fun. So we use these numbers to actually describe the pattern we're interested in, but we still do the repeated sample to address the methodology we have a concern for. Cool? Another thing I'm trying to do is introduce you guys to results where you're actually using the result to test your overall research question, but then also results which are really about your methods that you still got to deal with. You still got to take a look at. You still got to know because they'll introduce and influence your overall question. Okay, permutation. Yep. Permukill. It's a more powerful type of permutation test. The actual variable you use, the function used, is AOV perm. But then you're putting in the exact same code. You're putting in your model. And you're putting in your same blocking variable. Error, parenthesis, site, replicate. Oh, Jordan, I made the mistake. I had too many parentheses. Well played. Replicate parentheses, comma, data df. Same code, same idea, but instead of doing a normal assumption for testing with a parametric test, be able to do a permutated test. Example is right there. Please do me a favor. Here it is with Permaco. Here it is with LN Perm. This time we're going to define our max number of iterations is 10,000 using max capital I TER. In this case, we're not defining it. Run them both, see how they compare.